The remaining part of this chapter is exam number 3 material. And in your study guide, there are practice problems for this remaining part of chapter 6. In this next part, we're going to learn how to read a chemical reaction a little better and try and understand exactly what it's telling us. You can read something, but what's the meaning? We learned in some material previously that a chemical reaction gives you a number ratio. And here's our example of a reaction we showed in a previous chapter. But this chemical reaction says that for every 1 glucose, there's 6 oxygen molecules that need to react. It's a number relationship. You could say for every 1 dozen glucose molecules, 12 dozen oxygen molecules react. Or pick any number unit you want and use the chemist's favorite unit, which is the mole, and you could say for every 1 mole of glucose, C6H12O6, 6 moles of oxygen are consumed. We can make this number relationship for any chemical reaction, and we make this number proportion by looking at the numbers that are out in front to the left of the formula of the chemical. You can do it for the reactants, you can do it for the products. So we could tag on the product mole relationships. So for this particular reaction where there's 4 different chemicals, 2 reactants and 2 products, you can make a mole to mole to mole relationship and use any combination to make some sort of conversion factor. This provides a lot of information. You could do it for any chemical reaction. You could do it for hydrogen reacting with oxygen to form water. In this reaction, for every 2 moles of hydrogen, there's 1 mole of oxygen. And for every 2 moles of hydrogen, there's 2 moles of water that form. Or the number of hydrogen molecules that react, it's exactly the same number of water molecules that are formed. But we can write this as a relationship. So here's the mole-to-mole relationship for the reactants, and you can tag along the water relationship. The mole-to-mole relationship gives you a valuable relationship that can be used to answer a lot of different questions. For example, if you knew how much hydrogen you had in a fuel container, you could calculate how much oxygen is going to be consumed. These mole-to-mole relationships, chemical reactions are like a cookie recipe or any recipe. It's a number relationship. So for example, say you had a cookie recipe where some of the ingredients, there was 1 cup of milk, 2 cups of eggs, 2 cups of flour, and you were really consistent when you made your cookies and you always made 12 cookies. And you knew each cookie weighed 50 grams. With all that information, we could make a relationship between all the different ingredients that are part of this recipe. So here is a set of relationships from units from our recipe. These are number units. And we could even put more on from our recipe. We know this recipe always makes 12 cookies. And 12 cookies, number units, you could say 1 dozen cookies. It means the same thing. This relationship, this recipe, would allow you to do a lot of things. It has a lot of usage. Say you wanted to make 24 cookies, how many cups of milk would you need? You could use this number relationship to figure this out, this recipe, this cookie recipe. So it's really good to eat cookies and talk about cookies, but we're going to look at the recipe of a chemical reaction. So instead of talking the language of desserts, we're going to talk the language of chemistry. We're going to use the chemical reaction and the number relationships that it provides to answer a lot of different types of questions. The process of using the chemical reaction and the mole-to-mole relationship that it provides to answer some questions, this process is called stoichiometry. It's a unit conversion problem. And like any unit conversion problem, you're given some information and this information contains units, and you're trying to go and figure something else out that has different units. In our beginning stoichiometry problems, you're going to be given some information, some quantity information about either a reactant or product. And you're trying to figure out how much of a reactant or product is either produced or used up. When we do this, the one we're given information about, we're going to call our A molecule. So as you read the story problem, you're given some information and you're going to label that chemical as our A. The chemical you're trying to figure out some information about, we're going to call our B. This is analogous to what we talked about with our cookie recipe. I said we wanted to make 24 cookies. That's our A. How much milk do we need? The milk would be our B. Shown on this page is kind of an outline of the stoichiometry problems that we're going to be looking at. Each arrow represents a conversion factor, and you'd be using a specific type of relationship. So here's our outline of stoichiometry. Notice there's A's and there's B's. When we first start out, we're going to be given quantity of the A. And the quantity you give, it could be pounds, it could be kilograms, it could be grams. No matter what quantity of A is given, you have to get it into mole quantity. I could say I had a gallon of milk, how many cookies could I make? My recipe says 2 cups of milk is used in this chemical reaction, this recipe of cookies. Well, I got to convert gallon into cups in order to use that cup relationship. For a chemical reaction, you have to get the A amount into mole quantity. That's because you're going to solve a question about how much of this B molecule is either used up or produced. In order to go from your A to your B, you need your chemical reaction. You need your mole to mole relationship, and that comes from your chemical reaction. RXN reaction. This is the heart of any stoichiometry problem that we're going to be doing in this chapter. You always do this step. You go between moles of A and moles of B. You will always use the mole to mole proportion in any of these stoichiometry problems. As far as the other units, well, what do we see? What are we going between? If we were going between grams and moles, what gives you grams to moles, oh, that's the molar mass. And that would be the molar mass of whatever the A is, whatever formula it is. If I was going between pounds and grams, well, that relationship, that's given to you in the information packet. Over here, if I was going from moles to grams, just like grams to moles, moles to grams, you would use the molar mass. But the B molecule is a different chemical. So you would use the molar mass of whatever that B molecule is. Okay, there's lots of arrows here. Some of the conversions we're going to do within this chapter. Some of them we're going to learn a little bit later. But we see some other conversions that you should kind of be familiar with, like the word density. We'll just see when those problems arise. We'll start out pretty simple to begin with some of the example problems, and then maybe they'll get a little more complicated. Before we proceed with some stoichiometry problems and using the recipe of chemical reactions, let's do a cookie recipe, and to show yourself that you can actually do this and probably do some of these calculations in your head. Let's use the recipe that we just talked about for our cookies. So we have this proportion for our cookies. 1 cup of milk, 2 eggs, 2 cups of flour makes 1 dozen cookies. So that recipe is our chemical reaction. Let's assume that 1 dozen cookies, when you make that, the mass of that is 600 grams. 1 dozen cookies equaling 600 grams, that's like molar mass. It's analogous to molar mass. The recipe is analogous to a chemical reaction. So let's ask a question. So here's the question. If you had 6 cups of flour at home, And using that recipe we just had on the previous page, how many dozen cookies could you make? The one you're given information about, that's our A. So that's our A. The cups is our A. Dozen cookies, that's our B. So in our chemical reaction, the flour, that's our A, and dozen cookies is our B. So I'm going to be a little anal, and I'm going to put in what units I'm starting with, what units I'm going to. So 6 cups of flour, that's how much I'm starting with. The proportion, 1 dozen cookies for every 2 cups of flour. And if we solve for the answer at this point, we could make 3 dozen cookies. Or you could do another conversion, that would be 36 cookies. What if the problem also wanted to know how many grams of cookies could be made? So we already have our B information, but what if it also wanted to know how many grams? So we'll put a little question mark there. So we need one more relationship where we're going to take dozen cookies into grams of cookies. How would we do that? Well, how much, we know we have 3 dozen cookies. Where's that relationship for? Oh, it's up here. This is analogous to molar mass. 1 dozen cookies equals 600 grams. So we'll take that relationship and make another conversion factor. 600 grams of cookies per dozen cookies. 3 dozen cookies, and our final answer, 1,800 grams. It's the same quantity, just a different unit. So the dozen to 2 cups, that's like the mole to mole relationship. The 1 dozen cookies per 600 grams, that's like molar mass. So if you can do this, and some of you may have been able to do this in your head, you can do any chemistry stoichiometry problem that we're going to give to you. You just got to get used to those units. Shown here is an example stoichiometry problem. We're going to do a few on the next pages. We have a balanced chemical reaction. To make your mole-to-mole relationship, it needs to be balanced. It's kind of complicated. There's lots of numbers before the formulas, but if we look at it, it says for every 2 of those fat molecules that reacts, 127 oxygen molecules are used up. And for every 2 of these fat molecules, this is an example of a fat molecule, you produce 90 carbon dioxide molecules. And that sort of makes sense. Well, it should make complete sense. These 45 carbons all become carbon dioxide. If you have 2 of those molecules, you need to produce 90 carbon dioxide molecules. With this chemical reaction, this balanced chemical reaction, you should be able to make a mole to mole to mole to mole relationship. There's 4 chemicals, and we use these numbers that are out in front to the left of the formula to make that. So go ahead and pause the video and make a moles relationship using this chemical reaction. So the units here, moles for each one, you need to be anal when you do make this. You can't just say moles. You have to include the formula of the chemical. It's not complete otherwise. But as far as the numbers that go in front of that unit, 2 for that C45H86O6 molecule, 127 for the oxygen, the 90 for the carbon dioxide, and 86 for the water molecules. You're going to use 2 of these when you construct your relationship, your conversion factor, when you do the stoichiometry problem. And that's going to take you from moles of A to moles of B. When you look at a stoichiometry problem, you're given information about one of the chemicals. The chemical could be the reactant or the product. But the one you're given quantity information about, that's your A molecule. the molecule you're trying to figure out some information about, that's your B molecule. So read the problem, pause the video, read the problem, and on the chemical reaction, label which one is considered our A and which one is considered our B. So, as you read through the problem, you have 7 moles of the fat molecule. That's our A. And if you read through the rest of it, calculate the number of CO2 molecules. CO2 is our B. So it just so happens in this particular problem, the A molecule is on the reactant side and the B molecule is on the product side. It doesn't have to be that way. They both could be reactants, they both could be products. The A could be on the product side, the B could be on the reactant side. But this is what we're given for this particular one. The oxygen information and the water information, we're not going to use that. We're not going to use that mole relationship. We're going to use just the A and the B. So when we make our mole to mole relationship, we'll use the carbon dioxide and the fat molecule. That'll be used as our proportion. So we've been given information, we figured our A and our B. What units are we starting out with? We're starting out with moles. And in the question, what quantity of the carbon dioxide do we need to figure out? What unit will be there? Well, it's also moles. So we're going from moles of one to moles of the other. So if we kind of look at our flow chart of units, we're starting here and we're going there. That arrow represents a conversion factor. This particular problem will only require one conversion factor. Use this as a guide. Use this flowchart as a guide to kind of help you as you go through it. You don't have to use molar mass. We're just going to use the chemical reaction and the mole to mole relationship to get to our final answer. Some of you could actually kind of look at it and do the problem without writing it down on a piece of paper. This says, if you look at the chemical reaction, for every 2 of those fat molecules, 90 of these are being produced. So if you have 7 reacting instead of 2, you should have a lot more than 90 carbon dioxides for your final answer. But you gotta always show your work. So go ahead and use this mole to mole relationship, make a conversion factor, and get a final answer. And when you do write this proportion, this conversion factor, like any other one, you have to include units. You have to include moles. And you have to include the formula of the chemical. If you don't, you'll get marked off. So make sure you're as anal as possible. So go ahead and pause the video, write the conversion factor, and get an answer. Here's the proportion, and it's always a good idea to cancel units, and when you look at it, moles of the C45 compound cancel with moles of the C45 compound. If you didn't write the formula, what goes on top, what goes on bottom, the 90 or the 2, you have to show your work, and you have to write the formula of the chemical. And as we do our calculation, the number you should get is approximately 315. Shown on this page is another stoichiometry problem. Read through the problem, determine the A and the B. So go ahead and pause the video, write that down, and then we'll take it another step. So as we read through the problem, the chemical that has information given, which is our A, is this fat molecule. The B, this time, is oxygen. So our B and our A are both on the reactant side. When you look at the problem, what units are you given and what units are you going to? We're given units, quantity-wise, in grams. So we're starting out in grams. And what unit are we going to? Well, we're going to grams. So if we kind of look at our outline that we've shown below, we're starting here and we're ending here. We're starting with a mass quantity and we're going to a mass quantity. It's going to require 1, 2, 3 conversion factors. And when we do this, remember the mole to mole, that's our chemical reaction to go from gram quantity to mole quantity of A, that's the molar mass of A, and the last one would be the molar mass of the B molecule. So we need three relationships. So this is the same chemical reaction, so we have our same mole to mole relationship from the previous page, but you do need to calculate the molar masses of both compounds. The triglyceride, this 45 carbons, 86 hydrogens, and 6 oxygens, that's quite a few. And just remember, when you do molar mass, it's the mass of 1 mole. And so for both of those, it's 1 mole equals. It doesn't matter that it's part of a recipe and that 2's there, it's still 1 mole. The mole to mole takes into account those coefficients. So pause the video, write the 3 relationships, and then we'll go from there. So here are the 3 relationships without the complete numbers. But the first one, this is our A, we need the molar mass of the A molecule, which is our C45H86O6 compound. The chemical reaction will give us the mole to mole relationship for our A and our B. And the last one we need is the molar mass of our B, which is oxygen. So the 2 molar mass is always 1 mole, and we've done it for oxygen before. Its molar mass is close to 32. For the fat molecule, around 723. And the mole to mole relationship, 2 moles of that fat, which is also called a triglyceride. I'll use that interchangeably. So as far as beginning, we'll start with this 454 grams. That'll be our starting number. So 454, and we'll keep all the units, all the digits that are in there, grams of the C45H86O6, and we need 3 conversion factors. We have the relationships, and we're eventually going to get how many grams of O2 is used up. So pause the video, plug in the conversion factors if you haven't already, and get an answer. And here's the conversion factors written the correct way, but it's still a good idea to cancel units, and grams of the C45 compound cancel with grams, moles and moles cancel for the C45 compound, and moles of oxygen and moles of oxygen cancel, and we're left with grams of oxygen. When you get your calculation, the final answer is approximately 1275.6 grams of O2. So what does this mean? So this is a chemical reaction that shows the breakdown of a fat molecule. And if you, in your body, metabolize 1 pound, 454 grams of a fat molecule, how much oxygen in the air would you use? So you would use about 1,275 grams, which is about 3 pounds of oxygen from the air. So this is information that you could use. It's an information that some sort of a nutritionalist would use, but they may do it backwards. They may monitor how much oxygen you're consuming that's going into your body, and then they could back calculate to see how much of a fuel molecule you're metabolizing. So there's lots of information that can come from a chemical reaction. And one last example problem. So go ahead and read this problem, mark your A and your B, and then decide what unit you're starting with, what unit you're going to. And this one doesn't require 3 conversion factors. It's only going to require 2. So know where you start, know where you finish, and it's a good idea to kind of make a flow of your arrows to decide, to kind of give an example of what you should be doing. So pause the video and start setting up your problem. Unpause when you want to check your setup process. So as we read through the problem, the one chemical we're given information about is a product. It's hydrogen. So hydrogen is our A. The one we're trying to figure information about is a reactant, and it's sodium. If this much hydrogen reacts, the question wants to know how many grams of sodium will be used up. If we look at our flow chart down here, we're starting here. We're starting with moles of hydrogen. So 0.979 moles of hydrogen. The next step is to figure out how many moles of B. So how many moles of sodium? There's no reason to work backwards. I mean, you don't have to use the molar mass of hydrogen. You're already given the number quantity. You can, once you have moles, go use the chemical reaction. Once you have moles of A, use the chemical reaction, go to moles of B. The problem wants to figure out how many grams of sodium are used up. You first, though, have to figure out how many moles are being used up, which is a number quantity, and it's perfectly acceptable amount of sodium. But the question wants you to get all the way to a mass quantity, so grams of sodium. So here's our flow chart. It's always a good idea to write something like that down. It's going to require two conversion factors. So start with the quantity of hydrogen that's being produced and eventually figure out how many grams of sodium are being used up. And here we have most of the work done. As far as relationship, here's the mole to mole relationship. It's, if you look at the chemical reaction, we assume it's 1 if you don't see a number. 1 mole of hydrogen and 2 moles of sodium. So the relationship is 1 to 2, but include the formulas of the chemicals. The molar mass of sodium, it's always 1 mole. So 1 mole of sodium is 22.989707 grams of sodium. So both of these relationships were put in as conversion factors. It's always a good idea to cancel units, but moles of hydrogen cancels with moles of hydrogen. And again, you got to put the formula of the chemical, and moles of sodium cancels with moles of sodium, and we're left with grams of sodium, the unit we're trying to go to. And when you do your calculation, it's really close to 45. 45.0 grams of sodium would be produced for when the quantity of hydrogen that reacts is 0.979 moles.